Let's talk about file formats. Files are ordered streams of binary data that have some method by which they have permanence. So a file could be written to a file system on your computer. It could be downloaded from the internet or uploaded to a various storage repository. So files contain data that are going to hang around between running of an application, etc. So a file is just a big bucket bag of data. It's not until we impose some structure on that data that it becomes meaningful. So for example, we might have these 90 bits worth of information, and we could imagine them as being pixels in a picture. But they might also just as easily be thought of as something else. They could be the compressed data of a zip file. They could be a stream of video. They could be a Word document. We don't know unless we apply some sort of structure to that data. This data could just be a stream. It's the exact same data. I drew it originally as a table of 10 by 9, and it seems to me that evokes the idea of an image or something. But if the exact same data is presented as a continuous stream, this may be a file that is a text file or a log file. It could be anything. So we need to imply structure. This is where file formats come in. File formats basically the set of rules or the specifications that give meaning to the data that's stored in the file. There are standard file formats. They exist so that when files are exchanged between people, there's meaning to that data. So if I format my file and follow the rules of creating a GIF file, when I send that GIF file to somebody else, they can use a standard GIF viewer and get meaning out of my data. I could take that GIF file and send it to a text program and force the text program to open it, and it's going to look like gibberish because the information, both being binary, are interpreted in different ways. So there are many, many standard file formats out there. You can also create custom file formats. If you have a need that doesn't exist in one of the standards, you're going to generate your own algorithms, your own rules for opening, saving, and opening those files. So a lot of times custom file formats meet some need that doesn't exist already. And then through wide use, if people begin to use that file format, it becomes a standard. Uh, if it's widely used enough, people will follow through on what is a typical standards process where it goes to a committee or a group or research group, and they establish what the official standard is for that particular file format, and then it's published so that everybody that wants to then consume information in that file format can follow a set of fixed rules. Of course, there's always revisions. So file formats are actually really defined to some extent by the algorithm that reads and writes them. The specification is written in a way that you can then implement algorithms to read and write these files and understand what's in them. Some file formats also then specify beyond the algorithm that you use to read and write the file, physically read and write it. There's also the algorithm that is used to interpret the data that's inside that file. Some files formats have a very specific algorithm. They only allow one, and others allow multiple algorithms to be used. A good example of that would be the zip file format. You can zip information, compress it together, and store multiple files in a zip file. And you have lots of options as to which algorithm for compression were used. That information then is stored in the zip file itself. When it's sent to somebody else, it has to tell the other zip program which algorithm was used to compress the data so it knows which algorithm to use to extract the data. Most of the time, this extra information, this metadata, is stored in a file header. There's some structure associated with the file header in the specification that tells the decoding application how to interpret what the content data is in the file. These headers might include things like, if it's an image file, you might have the height and the width. So you can decide what's a row of pixels and what's a column of data. How many pixels are being used per, or how many bits are being used per pixel in terms of color. And if you think of, say, a zip file, it's how many files are in there? What are they named? Where do they start and they stop? Which algorithm was used to compress the zip file? This is all metadata that is in a different section of the file than the actual content data. So in order to illustrate how file formats work and how file specifications work, let's develop one. We're going to call it the weak file format, or the WIF file. And the goal here is a WIF file is going to store black and white image data, and that black and white image data is going to be potentially compressed by a couple of simple run length encoding algorithms. Please note that this WIF file is a horrible way to store and transmit black and white image data. It is intended to meet only one purpose, which is a very simple example. So please don't feel the need to comment on how inefficient the weak file format is. So we would need to define specifications. Usually there's a version associated with a specification document. So this would be WIF version 001. We're going to use characters to store our data. And so a B in the file will represent a black pixel, and a W in the file will represent a white pixel. We're going to need a file header. In this case, it's 14 characters long, and anything after that 14 characters is image data. The header is going to consist of 4 fields. The first field is the image width. It takes 5 characters. The second one is image height. It takes 5 characters. The third field is the run length encoding algorithm that was used. So it was 0 would represent no compression. 1 would represent the REL algorithm 1 compression method, and 2 would represent REL and compression algorithm 2. If you want to see those algorithms, they are presented in the video on compression. And then the WIF version is going to be 3 characters. In our case, it'll be a 001 since we're working with WIF version 001. So let's go ahead and use that specification and see if we can write a decoding example. So let's see what a WIF file looks like. Here is our initial WIF version file. It's a stream of character data. So this could be edited and written in a text file, for example. We need to apply the standard in order to interpret what this means. So if we look at those first 5 characters, remembering that the standard said the first 5 characters in the header is the image width, we can see that the width of this image is 10 pixels. Next group is going to be the height, 9 pixels. So we can think then that this data is going to fill a grid that is 10 by 9. It was compressed with compression method 2. So when we decompress the data, we have to apply that algorithm. And here's the data. It's all of the information that is after the 14 character header. So I should apply run length encoding. So the W appears 22 times, the B appears 2 times, W appears 22 times, or 2 times, etc. So if I decompress that and begin writing out 10 items at a time to rows, I can decompress and get my image file.